Hello friends and welcome in yet another lecture of digital communication. In previous lecture we have completed ADM and CVSD. Also we have completed our comparison between DM, ADM, PCM, DPCM and CVSD. In this lecture we are going to see the two different source coding techniques, their method and the numerical based on those two methods that we have seen. Let's start with the content. As a learning outcome from this lecture, the students will be able to comment on the necessity of the source coding and optimize the redundancies in source information. They will also able to explain the procedures of Shannon-Fano source coding technique and algorithm and procedure of Hauffman source coding. Before start with the Shannon-Fano and Hauffman source coding, we will see what is the source coding actually. Let's say that a source generates the S number of signals. So the source encoder is having a task of mapping every signal S into some bit stream B. But always the communication system is having a problem for conveying the source data with the highest fidelity possible without exceeding the available bit rate. Or we can say that the source data has to be conveyed using the lowest bit rate possible while it maintaining the specified reduction fidelity. And that's why for every communication system there is always a trade-off existing between the bit rate and the signal fidelity. That means if I am increasing the signal fidelity, then the bitrate has to be decreased. Or if the bitrate is increased, then the fidelity of the signal is going to decrease. And so there should be the ability of a source coding system which has to do the suitable choice of a trade-off, and this choice of trade-off is nothing but coding efficiency or rate distortion performance. In this due lecture we are going to see all these concepts of source coding, coding efficiency, and how to get the adjustment of the trade-off with the help of the different types of source coding techniques. So every source coder is having a task to represent the given signal with the minimum number of binary symbols without exceeding the acceptable level of distortion, and this is determined by each and every individual application. There are two different types of source coding techniques. First type of source coding technique is said to be lossless coding technique. As the name indicates, the losses will be less in that coding technique, and because of that, exact reconstruction of the original source data is possible from the compressed data. This type of coding technique is going to provide reduction in the bit rate of the compressed data will be less as compared to the original data. But this will happen only if the given signal contains dependencies or statistical properties which can be exploited for the data compaction. This type of coding is also termed as a noiseless coding or entropy code. This type of coding is employed on discrete amplitude and discrete time signals only. The best example for this will be the joint photographic effect group, that is JPEG compression, which is used both for image and audio. The next type of coding is lossy coding. This lossy coding, as name tells us, it will have loss of some of the information, and because of that we are saying that it is characterized by an irreversible loss of information. And that's why here only the approximation of the original source data which is to be reconstructed is obtained. The exact reconstruction of the source data is not possible in this case of lossy coding. Even though this is true, It is said to be the primary coding type for the compression of speech, audio, picture and video signals. So here the example for the lossy type of coding is the JPEG for still picture coding, H.262 or MPEG-2 which is used for video signals, H.264 or AVC for video coding also. Now yet another concept is involved, that is variable length coding. So here in this figure we are observing that a discrete memoryless source is present. The meaning of that is the number of symbols which are to be generated by this source will not dependent upon what previously has got generated. Also, it is individually going to generate the different symbols at the different timings, and that's why this is called as discrete memoryless source. This discrete memoryless source is going to generate the alphabets which are specified with zeta, and it will have sk number of sk will be the output, which is said to be the distortionless encoder output into the block of binary logic for zeros and ones, because source encoder is the task of taking the symbol and converting it into block of binary bits of zeros and ones, which is denoted by this B. A finite discrete source is always capable of defining the list of source symbols, which may be also referred as alphabet, and with every alphabet its probability is associated. Let's say that this source generates the k different symbols. So for the kth symbol, which is indicated as sk, will have the probability of pk, where this k value is going to change between 0 to k minus 1. In some of the source symbols which are more likely to occur, that means their probability is more, they will have the short code word representation, but whenever the source symbols are rare to occur, they will need the long code words for their representation. Please remember this thumb rule when we are going for the source coding technique. Yet another term involved is code length. Code length is represented by LK, and this code length is nothing but the length of the binary code word assigned to every symbol SK, and this will be represented in terms of bits. The average code word length of the source encoder will be defined as rho is equal to summation for k equal to 0 to k minus 1 pk lk, where this pk stands for probability of kth symbol and lk stands for the code length for kth symbol. And as that source is capable of generating 0 to k minus 1 number of symbols, so its summation limits are from 0 to k minus 1. So every source encoder will have the input as a source symbol, and that source symbol will be converted into binary sequence of zeros and ones. That means input for source encoder is symbol and output will be the code word. This row represents the average number of bits per source symbol which are used in source encoding process. There is one another term which is expressed as row minimum, and this row minimum denotes the minimum possible value of the row, that is average number of bits per symbol. The third concept associated with the source encoding is coding efficiency, and this coding efficiency is the ratio of minimum possible value of row, that is average number of bits per symbol, to the average number of bits per symbol used in the source encoding process. And mathematically, this coding efficiency is represented as eta coding is equal to rho minimum divided by rho. In this case, if rho is greater than or equal to rho minimum, then coding efficiency will be always less than or equal to 1. That means for the condition of rho is greater than or equal to rho minimum, the coding efficiency for the source encoder approaches to unique. Now we will start with the first type of Shannon-Fano source coding technique. This source coding technique is said to be which provides the variable length source encoding. Let's go through the steps involved in this source coding technique. As a first step, we have to arrange the source symbols in the decreasing probability of order. In the second step, as per the given m value, that is whether the m is 2 or 3, we have to get the grouping of symbols to be done either in 2 groups or 3 groups based on m value, and these groups should be made in such a way that sum of individual probability of source symbol in each group will be nearly equal. If suppose it is a 2-level encoding, then we have to assign the digit 0 to all the source symbols contained in first group, and we have to assign digit 1 to the source symbols contained in the second group. But if the 3-level encoding is there, that is m value is 3, then for digit allocation or assignment to each group, we have to use -1, 0 and 1 correspondingly for first, second and third group. This type of division of groups we have to continue until every group will contain only a single symbol representation, and the assignment of binary digit or level for each of the subgrouping will also continue as mentioned in steps 3 and 4. This process we have to continue until number of times we are going to find out only one source symbol is existing in each of the group. Let's try for one example. So the given example comments on the source which is capable of generating 6 symbols with the probabilities of 0.40, 0.20, 0.12, 0.08, 0.08, 0.08 and 0.04. It is said that there will be 3 number of symbols in an encoding alphabet. So this line tells us about what is the m value, and here for this numerical m turns to be 3, and it is asked that we have to create the Shannon-Fano source code word for each symbol. Compute the respective length of the code words for each of the given source symbols. We have to determine the average code word length. We have to determine the entropy of the specified discrete memory left source, and we have to also determine the coding efficiency. So as per the given steps, we have to rearrange the given symbols in the decreasing order of probability. In this table, first we will arrange the symbols S0 up to S6, then corresponding symbols probabilities we have to arrange. But in the given numerical, the probabilities for the given symbols itself are in decreasing order, but if suppose in the given numerical the probabilities are not with decreasing order, we have to write the symbols here in the table also with the decreasing probability order. Once we have done this writing of first 2 columns, we have to go for first level arrangement to be done. In the second step, we want the groups to be made which will be of equal probability, but we have to make the number of groups equal to the value of m, and for this numerical the m value is 3. So we have to get these given probabilities to be divided into group of 3 which will have equal probability value. Let's say This is 0.40, 0.20, 0.12, 0.08, 0.08, 0.08 and 0.04. We may do the grouping as this as a 0.40. The yellow marked groups will be of 0.32. This mark, that is brown marked group, which will be of this 3 will be 0.24 and this 0.04, that is 0.28, which will be of nearly equal probability. So first group is marked with red, second with yellow and third with the brown. Here now, after getting the grouping to be done, we have to assign the digits to each of the group. So first group involve only one symbol. It is marked with -1. Second group consists of these two symbols. It will be marked with 0, 0. Then third group consists of these 4 number of symbols. These all will be marked with 1. After that, we have to go on subgrouping these given symbols with the equal probability of group. Now let's go for this first group. In the first group, only one symbol is present, so it will be kept as it is. In the second group, we are having only two symbols, but our m value is 3. As per the m value, we have to have 3 groups, but here only two symbols are present. So we are going to make only 2 groups out of these 2 symbols. They will be nearly equal, that is 0.20 and 0.12. So for this yellow marked group, in the next level, the digit assigned will be -1 and 0. Let's go for this third group, which was consisting of the 4 symbol values. These are 0.08, 0.08, 0.08 and 0.04. Again, m value is 3. So subgrouping should be done in such a way that there should be the values which will be containing into that, which will be of nearly equal probability, and the number of groups made should be 3. So let's have a grouping as this 0.08 will be one symbol, second symbol will be this another 0.08, and the third symbol we are going to have the group of these two symbols, that is 0.08 and 0.04. You can also go with the consideration of 0.08 and 0.08 as a separate group, and here these two groups of symbols we have made as a one group. Now for this 0.08, in this subgrouping we will assign the digit as -1. For this another 0.08, we will assign the digit as 0. And for these remaining 2 bits, 2 symbols, we will assign the digit as 1 each. Now in this subgroup, only one symbol is present. In this subgroup also only one symbol is present, but in this subgroup we are having 2 number of symbols. So again we have to go for third level differentiation of the given group. M is 3, but here only 2 symbols are present. So we will have the subdivision which will consist of one symbol as 0.08 and another symbol as 0.04. So let's assign the digits as -1 and 0 to these symbols. Now, how to get the code word for this, as we have come up to the stage where for each of the group only one symbol is existing. So we will see from the first symbol. Now for this 0.40 as a symbol, we are having only the digit assignment as a -1. So the code word associated with this S0 will be -1. For this second symbol with the probability of 0.20, the assigned digits are 0 and -1, so its code word is 0 -1. for the second symbol of 0.12 probability, the assigned digits are 0 and 0, so its code word is 0, 0. For first 0.08, that is S3 symbol, the assigned digits are 1 minus 1, so its code word is 1 minus 1. For second 0.08, that is fourth symbol, assigned bits are 1 0, so its code word is 1 0. Next 0.08 probability of S5 symbol has assigned digits as 1 1 minus 1, so its code word is 1 1 minus 1. And finally, for the sixth symbol with probability of 0.04, the assigned digits are 1 1 0, so their code word is of 1 1 0. Now let's check the length of the code for each of the given symbol. So the first code word consists of only one bit, so its length is 1. Here for second, third, fourth and fifth symbol, we are having 2 digits each, so their length will be 2. While for this fifth and sixth symbol, the length will be 3. This is how, from this table, after arrangement of the given symbols with the decreasing order probability, we will do the first level, second level and third level grouping as per the step we are finding that every group will have single symbol representation. And in each level, we will get the assignment of a binary digits to the individual group. Then the total code word for the given symbol will be found out. After finding the code word, we are writing for the code length based on how many number of bits are present in each of that code word formation. Now let's go for finding out the average code word length. As in this given problem, the k value is equal to 7, which is going to vary from 0 to 6. And that's why here with the equation where summation limits will change from 0 to k minus 1, for this problem k is 7, so limit will change from 0 to 6. That summation is corresponding to pk into lk, where pk is probability of that given symbol and lk is the code word length for given symbol. So we can expand this summation as P0L0 plus P1L1 plus P2L2 plus P3L3 plus P4L4 plus P5L5 and plus P6L6 as k varies from 0 to 6. Now for each of these terms from the given data, that means from given table, what we have obtained in last step, we have to take the values and substitute here, and finally we will find this row value as 1.72. So this will be having unit of bits per symbol because it is average code word length, and code word length will be defined as number of bits per symbol. Next step is determining the entropy of the specified discrete memoryless source. And the entropy will be found out as h of zeta is equal to summation from k equal to 0 to k minus 1 pk log of 1 divided by pk. pk's are nothing but individual symbol probability. As in this given numerical k is equal to 7, so this k value is going to vary again from 0 to 6. So this expansion of summation can be written with this particular given statement. Again, for each of the probability from the given data we will substitute the magnitude, and finally by doing all this process we will find out the answer of h of zeta is equal to 2.42 bits per symbol value. But friends, please remember that when we are doing this process on Calc, we are calculating the logarithmic value with the base of 10. That is natural logarithm we are going to calculate. But we have to have the calculation answer for this entropy in terms of bits per symbol. And that's why here the basic step what we have to remember is, after doing the calculation of this step for logarithmic function of base 10, we have to get this whole addition to be done, and finally to that answer we have to multiply with the value of 3.32. This 3.32 will give us conversion from to the base 10 value converted into to the base 2 value, that is in terms of bits. So please remember this multiplication finally to be done to get the answer in terms of bits per symbol value. Please remember this step, because here even though it is written log 2 on calculator, we are doing that for log 10. Next step is calculation of coding efficiency. So we are having equation of coding efficiency in terms of percentage is given by entropy divided by average length of code word into log of m to the base 2. So we have calculated this entropy, we have calculated the average length of symbol, and m value provided is 3, so these all values will be substituted over here, and this calculation we will find out as 88.7. And again please mind that here the log of 3 has to be calculated to the base, so the same procedure on Calc, log we are going to do with the base of 10, multiply that with 3.32, and here we will find out the final answer as 88.7 for the coding efficiency. I think friends you have understood the process of getting the Shannon-Fano source coding. Now we will go towards the second type of source coding, that is Hauffman coding. In Hauffman coding, to comment on the procedure, the general steps will be the given set of source statistics of the discrete memoryless source is to be replaced with the simpler one. So here the set of source has to be replaced by the simpler coding value, and this reduction process will be going to continue in step-by-step manner until the final set of source symbols will be less than m of an m-array coding, which will be giving the optimal code. Once this process is completed, we have to trace in backward for finding out the optimal code, which is named to be Hauffman code. So in detail the steps required for that Hauffman coding we will go. As like Shannon-Fano coding, the first step is writing the source symbols in decreasing probability order. Then once this will be done, we have to assign the binary logic 0 and binary logic 1 value to the two source symbols of the lowest probability in the list obtained by doing the first step. This will be said to be the splitting stage. This is true if m is 2, but if m is 3, we have to assign the binary bits of -1, 0, 1, and we have to use the last 3 source symbols for this, after doing the arrangement of probability order in decreasing value. The third stage, we have to combine the probability of last 2 or 3 source symbols, and let's regard it as new source symbol with the probability which will be equal to the sum of those 2 or 3 number of source symbols. Then we have to place this assigned probability of the new symbol in the list accordance with the rest of the symbols with their given probabilities. But while doing this, we may have two conditions. Either the newly obtained symbol probability will be higher or lower than as compared to given probabilities which are existing in the given source set value, or there may be consideration that the given obtained probability will be equal to any another existing probability in the given set. If this is true, then with respect to the equal value, the obtained value will be either placed at higher location or lower location as compared to the original equal. As a fifth step, we have to repeat the given procedure from the step number 2 to 4 until every set will consist of only m number of symbols. Again, for each of that repeated procedure, assignment of binary digit of 0 1 or -101 has to be done, and this process will be called as formation of Hauffman. And finally, we have to determine the code word for each original source symbol by working backward and tracing the sequence of binary logic values of zeros and ones assigned to that symbol and as well as its success. Let's try for a numerical. So in the given numerical, the discrete memoryless source which is generating 5 different symbols with the probabilities of 0.1, 0.2, 0.4, 0.1 and 0.2, we have to calculate and create the Hauffman tree which will follow the standard algorithm, and we have to compute the code word for each of the given source symbol. We have to find out the length of the code word. We have to determine the average code word length, and also we have to determine the entropy of the specified discrete memoryless source, and finally we have to comment on the. So let's start with the formation of Hauffman. So to form the Hauffman tree, the first step is arranging the given symbols with their decreasing probability. So here the highest probability is of 0.4, next probability is 0.2, zero point 0.2 and then 2.1 value. So let's form the step 1 with the decreasing order. So we will find out the symbol S0 with 0.4, S1 and S2 with 0.2 probability each, and S3 and S4 will be also with 0.1 probability. Now in this problem, it has not given with the specification of m value. So let's take the m value as, if m value is 2, we have to consider the lower two symbols, and for these two lower symbols the digit value of zeros and 1 will be assigned. After doing this, the next step is we have to combine the probability for the lower two symbols. So the probability when combined for these two symbols, it will be again 0. And as we have said in the step that if suppose this combined probability is equal with the previous remaining probabilities, then either we can place this combined probability before these two probabilities or after this probability. So here we are using the higher placement corresponding to equal probabilities which are originally existing. You can write that at the lower place also, but the consequences for the placement will be different. That we will discuss in the next coming. So here we are placing this combined probability at the higher place, and we are taking these remaining probabilities as, so this will be our fourth step. Now we will continue the process of taking the lower two symbols, assigning the digits for that, and again recombining that two lower symbols, placing that with the proper order of probability value. So in first step we have got this arrangement. In the second step we have placed this with the higher location. Now in this step the lower two probabilities we are considering, which are with value of 0.2, then we are assigning 0 and 1. The combined probability for these two symbols, lower symbols, will be of 0.4. As in the previous stage, we have used the higher placement with the equal probability value. The same we have to follow if the equal probability is existing for the next coming steps also. So as per this rule, we are placing this combined probability 0.4 before this original probability of 0.4, and we will carry forward this previous 0.4 and 0.2 value as it is in the next step. Again in this fifth step, the lower two probabilities we will take. We will assign the symbols 0 and 1 to the lower probabilities. We will combine these probability values. They will be coming to be 0.6, and here the 0.6 will be carry forwarded in the numerical. So let's make a correction over here. It should be 0.6, friends. It should not be 0.4. So let me do the correction over here. Sorry for that mistake. It should be 0.6. So this will be point. So this 0.6 and 0.4. Now as per our required condition, only two symbols are present. So this is our ending step. But at this ending step also we have to assign 0 and 1 to the symbols. Now after reaching to this step, we have to trace back for each of the symbol. What is the assigned code word for that particular symbol? So we'll start with the first symbol. The first symbol is 0.4. This 0.4 has been carried forwarded over here. This 0.4 is forwarded to here. Here the assignment is 0. Now this 0.4 is involved in the combined probability of 0.6. This 0.6 is present over here and it is assigned with the value of 0. So this 0.4 traversal is with this way, and the assigned values we have to track back in the order. So this is your first value at 0. It is when traced back we are coming for this symbol as a 0. So we will find that this 0.4 will be having the code word as 0, 0. Let's go for second symbol with the probability of 0.2. It is traced out like this. Here it is assigned the value as 0. It is involved in the combination probability of 0.4. This is taken forward over here. Here is no assignment. This 0.4 will be again carry forwarded over here, but here assignment is 1. We have to write in reverse order the digit assignment. So 1 is written first. This carry forwarding we have to see, so it will be 0. So we are writing this code word as 1. Next is 0.2. 0.2 is carry forwarded with this place. This 0.2 is assigned with 1. It is involved in combined probability of 0.4. 0.4 will be taken over here. Here no digit assignment. This 0.4 is carry forwarded over here, and here it is assigned with the digit of 1. So in tracing back for the code word finding, this 1 we have to take. The tracing back will start over here. This 0.4 will be having the digit presence in previous step as 1. So its code word will be now 1. Now the next symbol with the probability of 0.1 we have to consider. Its assignment is 0. It is involved in combined probability of 0.2. it is carry forwarded over here. Here no digit assignment. Again it is carry forwarded to this point 2. Here digit assignment is 1. This is used in combined probability of 0.6, and this 0.6 will have the digit assignment as 0. So in tracing backward, the symbol 0 will be taken, digit 0 will be taken. It is backward traced. Here one digit is present. Again backward tracing will be done. Here this point 2 is assigned with this 0 digit. So we will have the symbol value as 010. Sorry, code word value as 01. For the last symbol, first digit assignment is 1. This point 1 is used in combined probability of point 2. This is forwarded over here. Here no digit assignment is there. Again it is forwarded to point 2. Here digit assignment is 1. It is used for combined probability of point 0.6. Point 0.6 will be forwarded over here, and here for this digit assignment is 0. So we will trace back for finding the digits assigned. First digit assignment is 0. The tracing is from this point 2. So 1 is appearing. This point 2 is traced back here. Again we are tracing back to point 2, and this point 2 is taken from point 1 with the assigned digit of 1. So its code word will be 011. Now let's find out the length of code word. Here the first, second and third symbol consist of two number of bits each. So the length for S0, S1 and S2 will be 2, while for S3 and S4 will be 3. Let's go for next steps. So here we have written the code word length as we have seen in the previous step. After getting this table, we have to go for calculating the average length of code words for each source symbol, which we have written as zeta is equal, rho is equal to summation k equal to 0 to k minus 1 pk lk. Here we are having 5 number of symbols, so k varies from 0 to 4. So here this equation has been expanded. Corresponding probability and the length values we are putting for each of the symbols from this given table, and we will able to calculate the value of rho as 2.2 bit. Then we have to determine the entropy for the given discrete memoryless source. For finding the entropy, equation is summation from k equal to 0 to k minus 1 pk log to the base 2 1 divided by pk. As k value here is changing from 0 to 4, so we will get the expansion of given equation like this. Substitute all the probabilities respective to the given symbols. Calculate the given answer for each of the sum term with log of 10, get the addition to be done, and finally multiply that answer with 3.32 to get the answer in terms of bits per symbol. Now we have to comment for the result, and that result we have to comment for the coding efficiency value that we are going to obtain. To get the coding efficiency, we have to substitute the values of rho and this entropy what we have calculated in previous steps. So here the coding efficiency comes out as only 3.67%. So in the previous step you have seen that I have said that if the equal probability value comes out by combining the probabilities, then we can place that probability either at the higher place or at the lower place. So There may be variations happening in Hauffman's source coding process to be obtained. And that's why it is said that the Hauffman source coding process is not a unique one, as its tree is going to change. And these tree variations may occur because of the two processes. One is due to the assignment of 0 and 1 that we are going to do at each splitting stage. And the second one is due to the combined probability placement if it is exactly equal to any other probability in the given list. So at each splitting stage, either I can assign the given probabilities with 0 and 1 or 1 and 0. So each individual encoder may do this task arbitrarily. And because of that here, based on your way of assignments, the resulting differences will be inconsequential. Then, due to the second reason, that is combined probability placement, if exactly equal probability is existing, either we are placing that at a higher location or at lower location. The results in codes for the various source symbols will generate the different code lengths, and the average code word length will remain the same, even if we will use the higher placement or the lower placement. So to prove this variation based upon the either of the case, we are going to see one another example and its effect on getting the code word and its code word length to be calculated. So let's take this example, which is one another example where now m value is 3 and we are having the symbols which are from S0 to S6. First step, arrangement of the given symbols in the decreasing order probability. Now as m is 3, the lower 3 symbols we have to consider. Here you can see in previous example we have used the ordering of these bits as -101, but here random ordering we are using as 10-1. So this may happen from different source encoder to source encoder, that the assignment of bits may go on changing. So one may use as -101 or other may use 10-1 also. Then carry forwarding this, the total probability for this will be 0.20. Originally here 0.20 is there, either corresponding to this original probability, combined probability will be placed at higher location or lower location. Here we are referring for higher placement. So 0.40 will be carry forwarded as it is. Combined probability placed as 0.20. This 0.20 will be carry forwarded. Then 0.12 is present and then this 0.08 will be present. As m is 3, again taking last 3 probabilities. Assignment here we have done as 101 -1 in the same order we have to place for next coming levels of reduction also. So we are writing the digits as 10-1. Again combine this probability. This combining will give the result as 0.40. Originally 0.40 is existing. Here in this step the higher placement you have used. The same type of placement I have to refer in the next level of reduction. So 0.40 will be placed at higher location. This 0.40 will be carry forwarded. Again 0.20 will be taken as it is. Now in this level of reduction, only 3 symbols are left. So here we have to stop. But before stopping, we have to assign the digits as 10-1. Now after stopping here, let's track for the code word for each of the symbol. So 0.40 taken over here. This point 40 will be taken over here. Only here the assignment of 0 is existing. So the code word for this source symbol 0 is 0. Its length is 1. Then the next symbol probability is 0.20. This has been taken over here. Assignment is of 1. This is involved in combined probability of 0.40. It has been taken over here. Assignment of 1. We have to trace back for the bits to be found in backward order. So first value is 1. This is tracked over here. We are tracking for first 0.20, so it is tracked with another value of 1. So its code word is 11 and length is 2. We will go for second symbol 0.12. 0.12 will be taken over here. It has been assigned with the 0 symbol value. It is used in this combined probability. Combined probability is taken over here. It is assigned with the digit of 1. We have to trace back. So 1, it is traced back for the 0.12, which is 0. So the code word for 0.12 symbol is 10. Length is of 2. Next we will go for this 0.08. Point naught will be carry forwarded over here. Assigned digit is -1. It is involved in combined probability of 0.40. 0.40 is assigned the digit as 1. It is traced back for the code word. So 1 is taken. 1. Then we are tracing for this 0.08. So it is with -1. Here no assignment. So we will find the code word for this 0.08 as -1 1. Next is this code word will be 1 -1. Next is 0.08. Here assigned value is 1. It is involved in combined probability of 0.20. No assignment of digit. Here 0.20 is forwarded. This is having assignment of -1. So its code word will be -1 1. Next is 0.08. Assigned value is 0. Involved in combined probability. Taken over here. This will be taken over here and assigned value is -1. So its code word is -1 0. Lastly, this symbol of 0.04 assigned with the digit as -1 involved in combined probability of 0.20 taken over here. It will be carry forwarded as it is and final digit assignment is -1. So the code word will be -1 -1. So for these all symbols, code words will be of length. Again, by using these two equations, we will find out the average code word length and the entropy, and finally by substituting these values in the equation the coding efficiency will be calculated. Let's check the effect of variation in the Hauffman coding based on either the random number assignment or based on the placement to be done for the equal probability value. So the first numerical we have checked out, which will be with the source probabilities of 0.4, 0.2, 0.2, 0.1 and zero point 0.1. In this calculation, we have used the higher probability placements. So here you can see we have used the higher placement. So instead of that, if I am using the lower placement, that means in the fourth step 0.4 will be present, but this combined probability we will taking after this 0.2 and this 0.2, which are originally with equal probability. And in subsequent steps also, if equal probability occurring, we are using the lower placement. So if we are doing this step, then it is called as second method for the code word calculation. So in that part, with the same processes, the code word obtained for the symbols will be 1, 0, 1, 000, 0, 0010, 00, 11. So let's check that for first symbol and up to the last symbol, the code words are going to change for each of them. At the same time, the length of the code word is also going to change corresponding to each of the symbol. But there is one notable thing, that either you use first method of code word calculation or second method of code word calculation, the average length of code word for each of the method comes out to be 2.2. That means any method of encoding we will use out, we will find that average length of code word will become equal to the same. Then the question arises in mind that which method is suitable or which method is efficient one, and the answer for that lies in this particular slide. So in that case, for every discrete memoryless source, we have to find out the variance associated for average code word length of the source encoder. So variance will be found out as sigma square x is equal to the probability of that symbol into the length of that symbol minus the average code word length bracket square plus next probability associated with the symbol, that symbol length minus the average code word length bracket square. And this like term we have to write for each of the number of symbols. Now let's try for the variance calculation for the first method. So in the first method, the average code word length is of 2.2, but the lengths we have to substitute for each of that case, probabilities we have to substitute, and we will find out that in first case the variance value comes out as 0.160, while in second case the variance value will come out as 1.928. So the final comment for choosing the type of coding is that from these two calculations we can see that sigma square 1 is less than sigma square 2. Here we have to choose that encoding method which will have less variance value. So we have to prefer the first method of encoding over the second method of Hauffman code encoding. So friends, I think you have got cleared with the two types of source coding techniques, their procedures, numerical solution, and what is the concept of source coding itself. So goodbye and happy learning, friends.